What is going on, everybody? Welcome to another lecture in linear algebra. So the last lecture that we talked about was with linear transformation. The good thing about that is we are done with linear transformation. So we're now opening up into a new chapter that is pretty much with orthogonal and inner product spaces. And before we start talking about like the inner product spaces and all that stuff, we are first going to talk about the length and the dot product in R of n. And so for those of you who probably heard of those two before, my guess is that you have taken a high school physics course because you talked about vectors. And so before we actually get into it, we're gonna actually do a little review on vectors, just a tiny one. And then from there we're gonna talk about the length and dot product. For most of you, if not some of you, this might be a little review, but the good thing, the good news about this chapter is that it's relatively easier than the last two. So like I said, we're gonna start with reviewing vectors, and the basic definition of a vector is a vector, or I guess a property of a vector is that it has both magnitude and direction. In terms of symbols, it's usually denoted with an arrow, well, a lowercase letter with an arrow, or it's bolded. It is commonly used in 2D or 3-dimensional spaces, which, I mean, you could go higher, but for you guys, it's something that you've seen when you're playing around with 2 dimensions or 3 dimensions in physics, more particularly. And so like a general picture of what a vector is we have an xy coordinate system, and we have an arrow starting from the origin pointing at some point. That point is 3, 2, and so that arrow is pretty much the vector. So yeah, that was pretty much a quick little rundown of vectors, and now we're going to talk about the length, which is what we have here, the magnitude. So the first thing we're going to talk about, well, first we're going to have to define a vector. So we're just going to let vector v be v1, v2, all the way to vn. And so its length, which as I discussed in the previous slide, is also known as magnitude or the norm, which is kind of a weird name. But the length or magnitude or norm, however you want to call it, is defined by like 2 absolute values of v. I guess that's how you could say it. And it is equal to the square root of v1 squared plus v2 squared plus all the way to vn squared. That is pretty much the length. It's pretty simple. And one thing that this tells us is that the length can never be negative because you're squaring every value and then you're taking the square root. And so when you square any value, it will always be positive. And we can have a length of 0 only if the vector itself is 0. And what each vector has, no matter the dimension, each vector has a standard basis that has a length of 1. And this is called the standard unit vector. And for those of you that have taken physics, have probably heard about this, or if y'all haven't, well, this is what it was called. But I'm pretty sure most of you that have taken physics recognize these standard unit vectors. And for the 2D and 3-dimensional cases, there are I and J for 2D, and then IJK for 3D. So I'm pretty sure, hopefully, that your physics teacher mentioned this, but these are called like the standard unit vectors, which is I, J, and K if you're working with 3 dimensions. And then another thing about, I guess, yeah, about the length of a vector is that if 2 vectors, let's say v and u, are in R to the n and are parallel to each other, then we can express one of the vectors as a scalar multiple of another. Because they're parallel to each other, they don't necessarily have to point the same direction. It just means that you can multiply one vector, so let's say u, by some constant such that it will give you the vector v. And this brings us with the length of a scalar multiple. So we're just gonna let v again just be a vector in the r to the n and c be a scalar. So that means the length of a vector that is multiplied by the scalar is simply just the length of the vector itself multiplied by the absolute value of c. And this makes sense because we're only looking at the length. Length has no negative number. Because we mentioned in the previous slide that the length can never be negative. So the scalar, it doesn't matter if it's negative or positive, it will always, you'll always take the absolute value, which forces it to become positive. Another thing that we have with vectors is this thing called a unit vector. And so a unit vector in the direction of v is simply a vector, but it will only exist if v is a non-zero vector in r to the n. So that means the unit vector, which we'll call u, would be equal to the vector divided by the vector's magnitude. And so what this gives us a vector that has a length of 1 and points in the same direction as v. That was pretty much it with lengths. So now, well, length of one vector. So what about like multiple vectors, as in the distance between two vectors? To find the distance between two vectors, well, it's simply given by the equation of duv, which is pretty much the double bars u minus v. And that's the same as taking the square root of the difference between each number of u and v and squaring it. So this is like very familiar to the length. The only difference is you're having a second vector and you're subtracting it, and then you're taking the square root. Again, because you're taking or you're taking the square and you're taking the square root, and because you're taking the square, again, this tells us that this distance can never be negative. And it can be 0. So this means that, yeah, the distance can either be greater than or equal to 0. And the only cases where it is equal to 0 is if vectors u and v are the same. And then another thing to note is that the distance between u and v is the same as the distance between v and u. So it doesn't matter which direction you're going, it is going to be the same thing. And so now we're going to talk about the dot product and the angle between two vectors. And the one thing to know about a dot product is a dot product is a scalar quantity. So it takes in an input of a vector, and it takes, and then comes out a scalar quantity, so just a regular number. Has no direction, so it is a scalar. So again, how do we find a dot product? Well, again, we have to define our two vectors. So we're gonna let vector u is equal to u1, u2, and all the way to un, and then vector v be v1, v2, all the way to vn. And so when we take the dot product, well, their dot product will simply be u dot v, which is how we write a dot product. Dot is literally a dot. And it is equal to u1 times v1 plus u2 plus v2 all the way to un times vn. And so in this case, we can get a negative number. We could also get 0, and we could also get a positive number. And now to find the angle between these two vectors, well, they first have to be non-zero vectors. And to get their angle is simply just the cosine of theta is equal to the dot product of those two vectors divided by the product of their individual magnitudes. And it's going to give you some number between 0 and pi. And so how do we get this? Well, I will show that in a linear shorts video. So this is something, if you're interested, I'll probably put a little card in this video once when I get the proof done and uploaded. But yeah, if you're curious or interested, feel free to watch that video. If not, if you want to take it as is, well, fair, it's your choice. So now this dot product that we've introduced has some unique properties, And the first one being is a dot product of UV is the same as a dot product of VU. And the reason why is because multiplication in just like real numbers is commutative. So when you talked about it, like when you were just little kids, you learn about multiplication is commutative. So A times B is the same as B times A. And same thing with addition. It doesn't matter how you add them, but it'll always be the same. And another thing about it is that it also satisfies a distributive property. So U dot vector V plus W, it's the same thing as adding both the dot product of U and V and the dot product of U and W. Another thing is when you bring in a scalar, which what we have is as C, and you multiply by a dot product, it is the same thing as taking one vector, multiplying it by that scalar, then taking the dot product of the other vector, and it doesn't matter which vector you multiply by the scalar first, it will always be the same thing. Again, is mostly because this is showing the property that multiplication is commutative with numbers. Another thing to note is if you take the dot product of the vector itself, you will simply get the length of that vector squared. And another thing about this is because you get the length of the vector squared, that means that if you take the dot product of a vector by itself, that means it will always be greater than or equal to 0. And to get the dot product of a vector itself to equal to 0, it will only hold true if the vector is 0 itself. And then I think the last thing is if you take the dot product of two non-zero vectors and is equal to 0, then that means both of those vectors are orthogonal. In other words, they are perpendicular to each other, which is a very unique property in the foreseeable future. And I think we will get to that later. We might get to that later, but this property will be useful in future classes. And so now we're going to move forward to our last thing, and it will be a couple of theorems. So again, before we start with the theorems, we're going to define both vectors v and u, and being in the r to the n. And so the first theorem is called the Catchy-Schwarz inequality. I think it's Catchy. I don't know. One of my professors calls it Coachy, I think, something like that. But I'm gonna call it Catchy. Catchy-Schwarz inequality, and this tells us that the dot product or the absolute value of the dot product of the two vectors will always be less than or equal to the product of the length of each vector combined. The next theorem is the triangle inequality, and so this is telling us that the length of two vectors combined will always be less than or equal to the sum of the length of each vector. And this is pretty much hinting at a very similar theorem when you took geometry, when they talked about triangles, in which a triangle only exists if the longest side is always less than or equal to the sum of the two shorter lengths. And so this is pretty much the same thing, and the only difference is we're talking about it in terms of vectors. And then lastly, because we have the triangle inequality, we can, and it's like kind of referencing triangles, then of course we gotta bring the Pythagorean Theorem, which tells us that the sum of the two vectors, or the length of the sum of the two vectors squared, is equal to the length of one vector squared plus the length of the other vector squared. And that is pretty much all for this video lecture. So this week we're gonna do a couple of examples, which is not gonna be a lot. I'm talking about the lengths, the dot products, like finding them, and then also trying to find the angle between them, and then also doing a proof on the dot product itself. But until then, I will see you guys in the blackboard.